Okay, so now we'll prove some of the properties of minimal spanning trees. So the first property we are going to prove is um, that given a minimal spanning tree like this, okay, if we remove an edge ij from that tree, so let's pick up this edge, okay, from B to E as our ij edge. If I remove that edge from this minimal spanning tree, it's going to create two components. It's going to basically break the tree and create two components. One component will have these four vertices, and the other component is going to have these three vertices, as I show here like this. Okay, so these four vertices are now in one component connected through this three edges, and these three vertices are at one component connected using these two edges. So now if you look at this as a we can call this as a cut, because we basically have partitioned the set of vertices of the graph to two components, and so the two sets have vertices that are present only in that set, which means a particular vertex is in only one set, not in the other set. Okay, and so which means if you take the intersection of these two sets of vertices, it is an empty set, and the union of these two sets is going to be the set of all vertices, right? Okay, so we call that as a cut. Now across this cut we have one or more edges crossing this cut, right? Now the minimal weight edge in this cut, right, is 7, isn't it? And that edge is part of this minimal spanning tree. Okay, so which means if you have a minimal spanning tree, then each edge of that minimal spanning tree is part of an ij cut. Okay, so like this edge is part of an ij cut. What is that ij cut here? These four vertices in one component and these three vertices in one component, and this edge from B to E is the minimum weight edge among all the edges in that cut. Okay, so how do we prove that? If this edge is not the minimum weight edge in this cut, which means there should be some other edge that is a minimum weight edge in this cut, if this edge is not the minimum weight edge. So we can as well use that edge and connect the two components and get back our spanning tree, right? So which makes what? Our initial assumption that we started with a minimal spanning tree. Remember, we started with a minimum spanning tree, removed that edge from B to E, got these two components, right? So if we now say that this edge that connects the two components as part of this ij cut is not the minimal spanning tree, then there should be some other edge, say this edge of weight, say 6, is could be used to connect these two components, and this edge is no longer needed, right? I could as well remove this edge, all right, and I can make this edge to connect the two components. Is that clear? So which means sorry, which means what? The word initial tree is not a minimal spanning tree. That's a contradiction, right? So which means every edge in a minimal spanning tree should be the minimum weight edge of a cut of its two end vertices, like this. Okay, the second property is very similar to this. It's the other way. The first property starts with, given a minimal spanning tree, we prove that every edge in the minimal spanning tree is part of an ij cut. The second property states that for a given graph, if you have an ij cut like this, okay, where you partition the vertices of the graph into two components like this, such that each vertex is in only one component. The union of the two set of vertices gives you the overall set of vertices, and the intersection is an empty set. Okay, same thing. If you have such a partitioning of the vertices, then again among the edges that cross this cut, the minimal weight edge that crosses this cut should be part of some minimal spanning tree, right? That's a theorem. So if you have an ij cut, the minimal weightage that crosses the cut should be part of some minimum spanning tree. There could be more than one minimum spanning tree for a graph, especially if the graph does not have unique edge weights. Now, in order to prove that, let's assume the contradiction that the minimal weight edge of this ij cut is not part of any minimum spanning tree of this graph. We want to again argue whether such a thing is possible, right? So this minimum edge weight, which is 7, is not part of any minimal spanning tree of this graph. If that's the case, then all those minimal spanning trees have some other edges, one of these other edges that cross this cut. But we know that all of these edges have a weight that is greater than or equal to the weight of this minimal edge weight, right? So we could as well remove that particular edge, which is actually connecting the two components, and connect the two components with this edge like this. That would make what? All those minimum spanning trees actually not minimum, because by removing the one of those edges that crosses the cut and replacing them with this edge, we are going to reduce the weight of those spanning trees, so making them not minimum spanning trees to start with, which is again a contradiction. So that goes on to say that if you have an ij cut, the minimal weight edge of that ij cut should be part of some minimal spanning tree of that graph. Okay, so we'll stop with this.